Howdy, today on Flippin Science we're comparing fuels.
Give me fuel, give me fire, give me that which I desire. Whoa!
So science understandings we're going to look at. Fuels, including fossil fuels and biofuels, can be compared in terms of their energy output and the nature of products of combustion. Calculate the quantities of heat evolved per mole per gram per litre for liquids and for the complete combustion of fuels, and compare fuels given appropriate data. So we're going to look at energy in a second, but the first part you need to look at is comparing fuels in terms of it says here, the nature of the products of combustion. So we're going to compare different engine types here because we have some data. So let's have a look at the data. So it's showing diesel engine cars versus petrol cars and electric cars in the UK. So we've got in London, in outer London and in rural areas. So we can have a look at the impacts in terms of the output of the combustion. Now obviously the electric vehicles aren't combusting anything when they're running, but if the energy used to produce the electricity that charges the electric cars is produced by burning coal, then you can count that. So let's have a look. If we look at diesel in the in London, we can see we get a lot of greenhouse gases being produced, that's this brown colour, and we get a lot of NOxes. So this is nitrogen monoxide, nitric oxide, nitric dioxide, N2O, dinitrogen monoxide, and all those NOxes, all those things together. We're not seeing too many fine particles, so this is 2.5 micrometer sizes. We can't really see that being produced here in this graph. But we can see the diesel's producing a lot more nitrogen oxides than, say, the petrol cars are in the same area in inner London. So because of that, we can see that comparing the output of combustion here, the diesel is worse in terms of nitrogen oxides than the petrol would be. And nitrogen oxides, they have implications in terms of things like acid rain. So we can look at data for different fuel types to see if the products of combustion are good for the environment or not as well. So when we're comparing fuels, we want to get the maximum amount of heat released per unit. The more heat you release from a fuel, the higher the theoretical power output from it. So in order to use the best fuel, we want to compare units of fuels so that we can figure out which one's the best. Because the more energy released, the better it is. We're going to compare in terms of moles, grams and litres for liquids. So let's do an example here. So let's compare the heat output of two fuels. We're going to compare hexane and octane. So here's hexane, here's octane. On the basis of these numbers alone, you would suggest that octane is the better fuel per mole because you're releasing more heat energy when you combust 1 mole of octane than you are when you combust 1 mole of hexane. So we saw before that octane is better per mole, but does that hold per gram? You never buy a mole of a substance, you buy grams or you buy litres. So let's start with grams. So to convert from kilojoules per mole into kilojoules per gram, we need to divide by the molar mass. So let's look at why we divide. We want to have kilojoules per gram as our final unit, and we're starting with kilojoules per mole. Now the unit of molar mass is grams per mole. Now, if we want to get kilojoules per gram, we need to turn this upside down so then we can cancel out the mole on the top and the bottom. So do that by dividing by, so it'll be moles per gram. That's the same as inverting here, that's the same as dividing. So if we cancel out our moles on both sides, we see that we get kilojoules per gram, which is the unit that we want to have. So I calculated the molar mass of hexane over here, I divided by the molar mass of hexane, and I got 48.44 kilojoules of heat energy being released per gram of hexane. So let's do the same for octane. So I need to calculate the molar mass of octane, so that's going to be 8 times 12.01, which is the molar mass of carbon, plus 18 times 1.008, which is the molar mass of hydrogen. So let's calculate that. So 8 times 12.01 plus 18 times 1.008, get 114.224, so we're going to divide 5,472 by 114.224. 114.224, so 5472.1 divided by shift answer equals 47.91 to 2 decimal places, so 47.91 kilojoules per gram. So on the basis of mass, so if we compare the heat energy being released per gram, that makes hexane a better fuel. Since we get 48.44 kilojoules of heat energy being released per gram compared to 47.91. So the issue is, when you buy fuel, you normally buy it per litre, not by the gram. So we need to be able to convert kilojoules per gram into kilojoules per litre. Now to do that, we need to use the density. You'll normally be given the density values for these to calculate it. Symbol for density is rho, so it's this, it looks like a P with that little stick above it. Now the density could be given to you in grams per milliliter, or it could be given to you in grams per litre. You need to be able to convert between those. That's fairly easy because there's 1,000 milliliters in a litre, so if we times that by 1,000, we will get 654 grams per litre. And it should make sense in your head, hopefully. If you have 0.654 grams in a milliliter, there's 1,000 milliliters in a litre, times that by 1,000, you get how many grams you get per litre. So, to find the energy density per litre, you need to multiply the energy density per gram by the density of the substance. If that density is in grams per milliliter, then you need to multiply by 1,000 as well, just for the reason that I showed you. So let's calculate the energy density of hexane in kilojoules per litre. So we have the energy density. Now I'm going to trust this calculation here. Normally I would do it myself so I don't get rounding errors. But I'm just going to do, start again, so minus 48.440, timesing that by the density, so that was 0.654, we had that before, 0.654. We're going to times that by 1,000 to turn that into litres. So I'm going to write that down as 31,700, round that down. So we go, so 31,700 kilojoules per litre. Now let's do the same for octane. So we need to find the density of the octanes. That was 917.917 grams per mil. So times by 0.917, times that by 1,000 to turn the kilojoules per milliliter into kilojoules per litre. And go to our calculator. So, and again, I'm going to have to reuse the number from before unless I can go back. Nope. We got 43,930. Over here, 43,930 kilojoules per litre. Now, I can put my minuses there to show that it's exothermic, but because this isn't a thermochemical equation, the negative, really we could just say that that amount of energy is being released per litre. Now if we compare our fuels, we can see that octane is a better fuel again per litre because it's more dense. You have more octane in a litre than you would for hexane, so therefore when you burn it you get more heat energy being produced. Let's compare some other fuels. So now we're going to compare two fuels. We're going to compare a fossil fuel, dodecane, and a biofuel, ethanol. We've got the enthalpy of combustion information here for dodecane, so minus 8,090 kilojoules per mole, and we've got its density as 0.750 grams per milliliter. But our enthalpy of combustion of ethanol, so minus 1,367 kilojoules per mole, on the density to be spicy, I've given it as grams per litre rather than grams per mil. In fact, that'll make it easier to calculate later on. So, on the basis of per mole, we would say that dodecane is a much better fuel. And this should make sense since it has a lot more bonds in it than the ethanol does, so that when we're combusting it, we get a lot more energy released because we're breaking a lot more bonds. So let's calculate the enthalpy of combustion of dodecane in kilojoules per gram. So we've got minus 8,090 kilojoules per mole. Okay, so we're going to divide that by the molar mass of dodecane. So that's going to be 12 times 12.01 plus 26 times 1.008. So let's calculate that in our calculator now. That equals minus 47.53. So minus 47.53 kilojoules per gram. So now we're going to take the kilojoules per gram, we're going to turn that into kilojoules per litre. So we've got 47.53 kilojoules per litre. And we're going to multiply that by our density in grams per milliliter. So multiply by 0.750 grams per milliliter. And we're going to multiply that by 1,000 because there's 1,000 milliliters in a litre. So if we go back to our calculator, and we get minus 35,647. So minus 35,648. So let's write that. Minus 36,648. And that is kilojoules per litre. So we've calculated for dodecane, let's calculate for ethanol now. So again, we're going to turn the kilojoules per mole into kilojoules per gram. So we've got minus 1,367 kilojoules per mole. Okay, we're going to divide that by the molar mass of ethanol, which is 2 carbons, so 2 times 12.01 plus 1, 2, 3, 4, 5, 6 hydrogens, so 6 times 1.008 plus 16 for oxygen. There's 1 oxygen there. So let's calculate that now. And I get 29.67, okay? So minus 29.67, that's kilojoules per gram. So now if we compare the dodecane with the ethanol, we can see that the dodecane is a better fuel per gram as well. Let's calculate the energy density per litre. So we're going to take the 29.67 and we're going to multiply that by a density. In this case it's nice and easy because our density is in grams per litre. We need to figure out how much, our unit is already in grams here. So because it's already in grams and our density is in grams, we just need to multiply it by, multiply those two together and we get our answer in kilojoules per litre because there is this many grams in a litre of ethanol. So multiply the answer by 789 and we get 23,412. So 23,412 kilojoules per litre. So again, per litre, dodecane is much better than ethanol. It's a much higher number, well, lower if we're using negatives, but a lot more energy is released per litre of dodecane than it is for ethanol. And this is one of the issues with using ethanol as a fuel, because it doesn't release as much energy per litre. You need a lot more ethanol to drive your car as far as dodecane would. Dodecane is present in diesel. So diesel cars usually go quite far because they have more bonds in their fuel. They break those bonds up, they get more energy per litre of their fuel, so they go further per litre. So this is one of the issues with ethanol cars. So now for Flippin Science, we looked at calculating energy density of fuels. That's it for Flippin Science today. See ya.